In the last video, we had a large cloud of hydrogen atoms eventually condensing into a high pressure, high mass, I guess you could say, ball of hydrogen atoms. And when the pressure and the temperature got high enough, and so this is what we saw in the last video, when the pressure and temperature got high enough, we were able to get the hydrogen protons, the hydrogen nucleuses, close enough to each other, or hydrogen nuclei, close enough to each other for the strong force to take over and fusion to happen and release energy. And then that energy begins to offset the actual gravitational force so that the whole star, what's now a star, does not collapse on itself. And once we're there, we're now in the main sequence of a star. What I want to do in this video is to take off from that starting point and think about what happens in the star next. So in the main sequence, we have the core of the star. So this is the star's core. And you have hydrogen fusing into helium. And it's releasing just a ton of energy. And that energy is what keeps the core from imploding. It's kind of the outward force to offset the gravitational force that wants to implode everything, that wants to crush everything. And so you have the core of a star like the sun, and that energy then heats up all of the other gas on the outside of the core to create that really bright object that we see as a star, or in our case, in our sun's case, the sun. Now, as the hydrogen is fusing into helium, you can imagine that more and more helium is forming in the core. So I'll do the helium as green. So more and more helium forms in the core. It'll especially form, the closer you get to the center, the higher the pressures will be, and the faster that this fusion, this ignition, will happen. In fact, the bigger the mass of the star, the more the pressure, the faster the fusion occurs. And so you have this helium building up inside of the core as this hydrogen in the core gets fused. Now what's going to happen there? Helium is a more dense atom. It's packing more mass in a smaller space. So as more and more of this hydrogen here turns into helium, what you're going to have is the core itself is going to shrink. The core itself is going to shrink. So let me draw a smaller core here. So the core itself is going to shrink, and now it has a lot more helium in it. And let's just get to the extreme point where it's all helium, where it's depleted. But it's been shrinking. It's much denser. That same amount of mass that was in this sphere is now in a denser sphere, in a helium sphere. So it's going to have just as much attraction to it, gravitational attraction, but things can get even closer to it. And we know that the closer you are to a mass, the stronger the pull of gravity. So then instead of having just the fusion, just the hydrogen fusion occurring at the core, you're now going to have hydrogen fusion in a shell around the core. So now you're going to have hydrogen fusing in a shell around the core. And let me just be clear. This isn't just happens all of a sudden. It is a gradual process. As we have more and more helium in the core gets denser and denser and denser. And so the pressures become even larger and larger near the core, because you're able to get closer to a more massive core, since it is now more dense. And as that pressure near the core increases even more and more, the fusion reaction happens faster and faster and faster, until you get to this point. So here, let me be clear. You have a helium core. All of the hydrogen in the core has been used up. And then you have the hydrogen right outside of the core is now under enormous pressure. It's actually under more pressure than it was when it was just a pure hydrogen core, because there's so much mass on the outside here. Trying to, I guess you could say, exerting downward or gravitational force down, trying to get to that even denser helium core, because everything is able to get closer in. And so now you have fusion occurring even faster. even faster. And it's occurring over a larger radius. It's occurring over a larger radius. So this faster fusion over a larger radius is then going to, the force is now going to expel, the energy that's released from this fusion is now going to expel these outer layers of the star even further. So the whole time, this gradual process, as the hydrogen turns into helium, or fuses into helium in the core, what's the hydrogen right outside of the core, right outside of that area, starts to burn faster and faster. It starts to, or I shouldn't say burn, it starts to fuse faster and faster, and over a larger and larger radius. So you might, the unintuitive thing is, the fusion is happening faster over a larger radius. And the reason that is because you have even a denser core that is causing even more gravitational pressure. And as that's happening, the star is getting brighter. And it's also the fusion reactions, since they're happening in a more intense way and over a larger radius, are able to expel the material of the star even larger. So the radius of the star itself is getting bigger and bigger and bigger. So if this star would look like this, if this star, maybe let me draw it in white. This star looked like this. Well, that's not white. This star looked like, what's happening to my color changer? There you go. Okay, this star looked like this right over here. Now, this star over here, since a faster fusion reaction is happening over a larger radius, is going to be far larger. And I'm not even drawing it to scale. In the case of our sun, when it gets to this point, it's going to be 100 times the diameter. And at this point, it is a red giant. And the reason why it's redder than this one over here is that even though the fusion is happening more furiously, that energy is being dissipated over a larger surface area. So the actual surface temperature of the red giant at this point is actually going to be cooler. So it's going to emit a light at a larger wavelength, a redder wavelength than this thing over here. This thing, the core, was not burning as furiously as this thing over here, but that energy was being dissipated over a smaller volume. So this had a higher surface temperature, higher surface temperature. This over here, the core is burning more. Sorry, the core is no longer burning. The core is now helium that's not burning. It's getting denser and denser as the helium packs in on itself. But the hydrogen fusion over here is occurring more intensely. It's occurring in a hotter way. But the surface here is less hot because it's just a larger surface area. So it doesn't make the increased heat is more than mitigated by how large the star has become. Now this is going to keep happening. And this core the pressures keep intensifying because more and more helium is getting produced. And this core keeps collapsing. And the temperature here keeps going up. So we said that the first ignition, the first fusion occurs at around 10 million Kelvin. This thing will keep heating up until it gets to 100 million Kelvin. And now I'm talking about a star that's about as massive as the sun. Some stars will never even be massive enough to condense the core so that its temperature reaches 100 million. But let's just talk about the case in which it does. So eventually you'll get to a point, so we're still sitting in the red giant phase. So we're this huge star over here. We have this helium core, and that helium core keeps getting condensed and condensed and condensed. And then we have a shell of hydrogen that keeps fusing into helium around it. So this is our hydrogen shell. Hydrogen fusion is occurring in this yellow shell over here that's causing the radius of the star to get bigger and bigger, to expand. But when the temperature gets sufficiently hot, and now I think you're going to get a sense of how heavier and heavier elements form in the universe. And all of the heavy elements that you see around us, including the ones that are in you, were formed this way from initially hydrogen. When it gets hot enough at 100 million Kelvin, 100 million Kelvin in this core because of such enormous pressures, then the helium itself will start to fuse. So then we're going to have a core in here where the helium itself will start to fuse. The helium will start to fuse. And now we're talking about a situation you have, helium and you had hydrogen and all sorts of combinations will form. But in general, the helium is mainly going to fuse into carbon and oxygen. And it'll form into other things and it becomes much more complicated, but I don't want to go into all of the details. But let me just show you a periodic table. I didn't have this in the last one. I somehow lost it. But we see hydrogen here has one proton. It actually has no neutrons. It was getting fused in the main sequence into helium. 2 protons, 2 neutrons. We would need 4 of these to get one of those, because this actually has an atomic mass of 4 if we're talking about helium-4. And then the helium, once we get to 100 million Kelvin, can start being fused. If you get roughly 3 of them, and there's all those other things that are coming and leaving the reactions, you can get to a carbon. You get 4 of them. 4 of them, at least as the starting raw material, you get to an oxygen. So we're starting to fuse heavier and heavier elements. So what happens here is this helium is fusing into carbon and oxygen. So you start building a carbon and oxygen core. So I'm going to leave you there. I realize I'm already past my self-imposed limit of 10 minutes. But what I want you to think about is what is likely to happen. What is likely to happen here if this star will never have the mass to begin to fuse this carbon and oxygen? If it does have the mass, if it is a supermassive star, it eventually will be able to raise even this carbon and oxygen core to 600 million Kelvin and begin to fuse that into even heavier elements. But let's think about what's going to happen for something like the sun, where it'll never have the mass, it'll never have the pressure to start to fuse carbon and oxygen. And that'll be the topic of the next video.